And the second talk is Aurelien Viterisi, Understanding the Limiting Factor of Solvent-Annealed Small Molecule Bulk-Heterojunction Organic Solar Cells.
Okay, thank you very much. So maybe I should mention that even though I'm from the University of Tarragona, this work was carried out in collaboration with a strong collaboration with the ICIQ, which is also in Tarragona. The main motivation behind this work was really to find a profound explanation on how such very subtle changes in the structure of a small molecule, I'm talking about small molecule solar cells now, and nothing to do with polymers, how such very subtle changes, like the position of an alkyl chain, for example, induce, and this is almost always the case, a very, very drastic change in the properties of the device you make with that donor. So to do so, we designed a family of donor molecule, which we based on the DPP-TBFU molecule, which was at the time a very popular one. And we swapped the N groups here for different electron donor groups and some acceptor groups. So we designed them in such a way that their optical property would be very similar. And as you can see, they all have like a very similar band gap. So that was done on purpose. So although they have very similar optical properties, they give rise to devices in which the efficiency and the characteristics are very, very different. Like, for example, like changing only one atom, like for example, changing an oxygen to a sulfur gives a very, very different efficiency. Sorry. We have over an 8-fold difference in JSC and almost a 2-fold difference in VOC. We find that the JSC almost never correlates the absorption of the active layer, and the VOC doesn't relate either, or doesn't show any trend between the experimental VOC and the theoretical VOC the calculated theoretical VOC. Moving on to the morphological characterization, in that case we see like very big differences. Like only looking at the AFM images, we see a very big difference in the texture, in the roughness. And if you corroborate these images with XRD measurements, you'll find that you're in the presence of crystallites almost in all the cases, but in some cases they're very small, and in some other cases they're very big, as in this case where you can even see them via AFM. Most of the crystallites seem to be quite well oriented, although you don't see it here, but they are. And in 2 cases, the blue molecule, as I will call it, and the green one, we've been able to characterize the way the molecules pack inside the crystallites, or in other words, the crystalline phase in which they crystallize, basically. This was done in a previous study. So to sum up, here is a side view of the active layer, how it might look like. And in most cases, we're in the presence of crystallites, more or less oriented, embedded inside an amorphous matrix of mixed material, mixed donor and acceptor materials, except in this case, and I'm coming to this case just right now. So, so these 2 molecules are probably the best one to exemplify how crystalline growth occurs in active layers of organic molecules. So they're very similar in structure, like they only differ from the position of the fluorine atoms on the benzene ring, and they start from a very different state before annealing. And when we apply an annealing to it, in this case I'm talking about solvent vapor annealing, they evolve towards like very different active layers. In that case, it remains almost similar to what it was before annealing, and in this case it rearranges completely to form these embedded crystallites inside the amorphous matrix. So it seems that crystalline growth is really the key determinant here, and we propose that it occurs via nucleation and growth mechanism. So here it should read a 4 here, I'm sorry. So according to that mechanism, the free energy change of the formation of a nucleus of a radius r is dependent on 3 factors, free contribution. The bulk free energy contribution, which is linked to the wave molecule pack inside the nucleus, or the crystallites, the growing crystallites, the strain energy, which I'm neglecting here, and the surface energy, which is linked to the energy arising from the interface between the growing nucleus and the amorphous matrix it is growing in. And so we've kind of quantified these free energy terms, and we get to that final profile in which the R radius, the critical radius, is the critical size of the nucleus to grow past it for the process to become favorable. So we see that actually our experience seems to fit quite well with this model, in which we observe that in case of the blue molecule, we always form larger crystallites than in the green one, and as in these profiles. And quite interestingly, like in one of the cases, it seems that growth is the rate limiting step, rather than in the blue, in the green molecule, nucleation the rate limiting steps. And this explains why in one case we can grow larger crystallites, no matter by exposing the active layer to a vapor of solvent for a longer time, rather than in the other case, like we're kind of limited to a size which we cannot grow bigger crystallites. So I'm coming to the conclusion. So it seems that the kinetics of nucleation and growth are the key determinant in forming the nanostructure and the crystallites in general. So these two terms are directly related to the molecular structure of the donors, and they're directly related to so any difference, any subtle difference in the molecular structure will have a big influence on these two terms. So I'm coming to the final question, like, is there a way we can predict how molecule pack or which phase they adopt in a given system? And so I'm happy to hear any suggestion, and my poster is poster number 17, and that's about it. I would like to thank all these people and these people for funding. Thank you very much.